Welcome back. We shall continue our discussion on how we can use the framework of statistical thermodynamics to understand the how we can correlate the contribution of underlying translational motion and internal structure in the case of an ideal gas. And we have already seen here that how we can write down the ideal gas equation starting from the Hamiltonian of the system. And here the basic exercise that we are performing is how to calculate the canonical partition function for this n particle system, and from there we are using the prescription of connecting capital Q, that is the canonical partition function, to the overall Helmholtz free energy of the system when the ideal gas is being maintained at a constant temperature, volume and a number of particles. The next property that we are going to look at is the internal energy, which from the equipartition theorem is known to be given by this expression, and that is nothing but the Joule's law, which says that for an ideal gas the internal energy is a function of temperature and temperature only. And for this purpose we have already started to look at how to obtain the internal energy starting from the canonical partition function Q, and here we have seen that ln Q is related to small q, and at constant volume and number of particles the dependence of ln Q on temperature arises entirely because of ln small q. And then we started looking at the different contributions of different degrees of freedom to overall small q, q trans, q electronic and q nuclear. Therefore, under the condition of constant volume and number of particles, we understand that any dependence on temperature of this ln small q will come either from this or from this term. And then we set out by writing the explicit expression for q trans and found out that del ln q trans del T under the condition of constant volume and number of particles is 3 by 2 T. Okay. Now, we will now go ahead and try and find out what is the corresponding contribution to the overall internal energy. Now, U trans is given by k b T square into del ln q trans by del T under the condition of constant volume and number of particles, and therefore, what I will write is this is nothing but 3 by 2 T into k b T square, and of course, I have a capital N from in front. So, that turns out to be 3 n by 2 k b T. Okay. So, now what I have here is this interesting observation that in my overall U, I have contribution from U trans plus U electronic and also if possible U nuclear. So, what is U trans? U trans is given by k b T square del ln capital Q by del T under constant volume and number of particles, right, and I show that this is nothing but n k b T square into del ln small q del T V n, and I have been able to show using the explicit temperature dependence of this small q term here because of translation. So, this is trans, this is also q trans, and what I find is that this is 3 by 2 n k b T. So, this is the result that we get from the equipartition theorem, but we also have some other terms appearing here. So, let us look at individually what these terms are, and we find that U electronic that is now being given by kBT square del ln capital Q or small q electronic del T, taking this derivative of constant volume and number of particles with a capital N in front. And in order to understand this, what I should be doing is I should be writing down what small q electronic is. That we already know is WE1 plus WE2 into e to the power of minus beta delta epsilon 1 2. Therefore, if I take a ln of this term, I will be taking ln of this entire summation. Then I am going to look at the temperature dependence of the logarithm of q electronic. Now, why should this term be dependent on q electronic? And that is because obviously I have this factor beta here. Where did I get this number from? This number we have obtained from the solution of the Schrodinger equation, and the solution has been obtained for an isolated system for 0 Kelvin temperature. So, that part is not temperature dependent, but explicitly the appearance of the term beta, which is 1 by kT, that governs the temperature dependent property of q electronic, and therefore, I can say that del ln q electronic del T, if I take this derivative under the condition of constant volume and number of particles, that is equal to 1 by q electronic into del q electronic del T under constant volume and number of particles, right. But as you see, q electronic is a function of beta. So, for the sake of doing the algebra, it is found that it is easy to write it as del q electronic del beta under the condition of constant volume and number of particles into d beta dt, right. Now, what is d beta dt? We already know that beta is 1 by kT. So, I must be having d beta dt as minus 1 by kBT square, right. And now, what is del q electronic del beta? That can be easily figured out from this expression. So, if I put this back, what I have is 1 by q electronic multiplied by the del beta of this term. The first term is independent of beta, so that drops out, and I have contribution from the second term, and the contribution is minus omega E2 into delta E12 into exponential minus beta delta epsilon 1 2, right. And then I have a multiplication again coming from this term, and that is minus 1 by kBT square. So, what does it give me? This gives me that u electronic, that is equal to n kBT square into del ln q electronic del T, keeping volume and number of particles constant, that would be given by 1 by n omega E2, then delta epsilon 1 2 e to the power of minus beta delta epsilon 1 2 into q electronic, right. So, we have been able to show what u trans is and what u electronic is. Okay. Now, think about what is q nuclear. So, once again q nuclear in this case is a constant term. Therefore, ln q nuclear is a logarithm of this constant term. Therefore, del ln q nuclear by del T under constant volume of number of particles, that is going to be equal to 0. Therefore, I can say that u nuclear here by assuming as a 0 of energy the ground nuclear energy state, I understand that there will be no contribution to the overall internal energy as measured in the by setting the ground nuclear energy state to be equal to 0. So, this would be given by capital N K B T square del ln Q nuclear del T V n, and this is 0. So, what is the net internal energy of the system then? The net internal energy of the system now is being given by an expression like this. Now, this is something very, very interesting, because as we see that in this expression I have first this green term that appears corresponding to Q trans. So, that is the contribution of the translational motion of the particles in the system, of the capital N atoms in the system, and there is another term over here that is proportional to capital N. So, for each particle I have this term appearing in over here, and this term is the correction to this equipartition value that appears because of the presence of a microscopic structure of the constituent atoms of the ideal gas. So, what we find here is we not only reproduce the equipartition theorem, but also we find out the correction that will be introduced as a result of the existence of the underlying microscopic structure of the atoms. The next thing that I will quickly go through is the entropy of an ideal gas. Now, the entropy of an ideal gas can now be determined very easily by looking by knowing the fact that I know U in terms of ln Q from ln Q, I know F from ln Q. So, if I take the difference and divide it by T, I should be getting the entropy S by definition. Okay. When you do this little bit of algebra, this is the expression that you get. So, what I have done is I have used the expression for U that I have derived over here. I have used the expression of F and then taken the difference, and this is what I write, and I am going to collect some of the numbers separately and give you the final expression as this. So, let us have a look at what these different terms are. I have taken this 3 by 2 NKB inside, and so these two terms combine together to give me the first term that I see here. Okay? And these two terms that appear here, they combined together to give me what I call is the S electronic, or the electronic contribution to the overall entropy of the system. Now, why do I say so? If we look at what S electronic is, we see that all the terms here which appeared here, which have been shown in the purple color, these are dependent on the electronic structure of the underlying atom. Okay? As a result, we would say that the contribution of the electronic structure is coming through these terms, and this is defined as S electronic. Now, what is it that I have here? Obviously, all the terms that I see here are coming from the overall translational motion of the atom as a whole within the volume V at a temperature T, and that is the contribution of this translational motion to the overall entropy of the system for n such atoms. And this equation is known as the Sackur-Tetrode equation, and we will have a look at the specific use of this Sackur-Tetrode equation, especially to understand what is known as Gibbs paradox, but that we will do later. At this point, let me also try to reproduce another property of the ideal gas, which we have repeatedly seen in our earlier exposure to the ideal gases, that is the chemical potential of an ideal gas. So, your preliminary studies on thermodynamics must have included this expression where you see that mu, the chemical potential, is a function of temperature and pressure. in general, and in the case of an ideal gas, this can be written as mu naught T, that is the chemical potential of the gas at a temperature T under standard conditions of standard pressure 1 bar, plus an incremental part which is kBT ln P. So, if the gas is present at a temperature T and volume and pressure P, in that case I should be able to separate out the entire chemical potential into two terms. One is what that is dependent on temperature only, and it is a fixed value under standard condition of 1 bar pressure, and there is an additional term which depends on the temperature and the pressure condition under which the gas is present. And the question that I ask over here is as follows: is it possible for me to start from the expression of capital Q and small q that I have used here and explain why an ideal gas should be having a chemical potential that whose expression separates out into two terms like this? So, what is mu naught T? In order to answer that question, what we are going to do is, once again we are going to use the definition of mu. So, what is the definition of mu? The definition of mu is, this is related to a derivative of ln Q with respect to capital N, keeping temperature and volume constant in the canonical ensemble. Okay? And then you multiply it with minus kT, and this is what you get as a chemical potential of a single component ideal gas, which is maintained at a constant temperature and volume. Now, if I want to evaluate this for the ideal gas, I write down that capital Q is equal to small q to the power of n divided by n factorial. So, what is ln Q? That is the quantity that I require. So, this can be written as capital L ln Q minus n ln n plus n. Okay. Now, under the condition of constant temperature and volume, I am going to find out what del ln Q del n is. So, I am looking for this particular derivative, and this would be given by the following condition, that I can write down that this is given by ln Q plus n del ln Q del n Tv minus ln n minus n into 1 by n plus 1. So, what I have done is, in the first term I kept n constant, I took a derivative with respect to n, keeping this constant. So, this is what I get. Then I kept n constants, took a derivative of this with respect to capital N. Then I took the derivative of these terms, and this is what I get. So, the result is del ln Q del n Tv, that is equal to ln. These terms cancel out, and so all you have is this is equal to small q by n. If that is so, then what is mu? Mu is given by minus kBT del ln Q del n Tv, and therefore, I can use this result and say that mu is equal to minus kBT ln small q by n, right. So, it is possible for me to write down that expression that mu is equal to minus kT, then natural logarithm of q by n. Now, please remember that in this expression I have assumed that this is 0. Obviously, small q, it is written for one particle and it is independent of capital N. So, that is the reason why I have been able to write it as 0. The next thing that I will do here is as follows. I am going to write down once again the explicit expression for small q. So, small q is equal to something like Q trans for a monatomic gas, Q trans, Q electronic and Q nuclear. Now, Q nuclear is a constant term, therefore, for the purpose of for our purpose we can neglect that. So, I am going to neglect it as a constant term. Therefore, I should be able to write mu as minus kBt ln small q by capital N, and the resulting expression is small q is 2 pi m kT by h square whole to the power of 3 by 2 into V e by capital N, right. And then I have minus kBt ln Q electronic by capital N, this term. So, this is a translational part, this is the nuclear electronic part. Maybe for the sake of clarity I can retain the Q nuclear there, no harm done. Now, please let us try and have a look at what are the terms that we have here. I know that V by N, this must be having certain relationship as far as the ideal gas is concerned. I know that P V is equal to capital N kBt. Therefore, under the condition where here I can write that V divided by N must be equal to kBt by P, right. So, what I do is instead of V by N, I will write this as kBt by P. Now, what I do is I take out this pressure dependent term. So, now mu is written as minus kBt ln 2 pi m kT by h square to the power of 3 by 2 into kBt into E, okay. And then this E will not be there because I am writing small q, and then minus kBt ln Q electronic into Q nuclear by N, then plus kBt ln P. Because I had P here in the denominator, there was a negative sign here. So, that gives me plus kBt ln P. Now, let us have a look at the two types of terms that we have obtained here. I have some term over here, plus I have some other term which has appeared as an additional correction to it. So, this term is the kBt ln P that we expect to have some moderation on the value of mu over and above what we see here. Now, whatever appears within this square box, that is dependent on temperature, okay. And as you see that this I could have written as kBt by P naught, where P naught is equal to 1 bar, and in that case this is nothing but mu naught T as defined in the literature. And therefore, what we have been able to do is, using the relationship between volume and pressure and N and T, we have been able to show that, well, my mu is going to be comprised of two terms. The first term is essentially dependent on temperature and the intrinsic properties of the system like M, Q electronic and Q nuclear. And what I am left with is this term kBt ln P, which basically tells me what mu naught T is. This is nothing but whatever appears here, and we obtain this kBt ln P as an additional term. So, what we have learned from here is as follows. So, using the formalism of statistical thermodynamics or molecular thermodynamics, we find that each and every thermodynamic function has a correction to it that appears from the underlying microscopic structure, and this correction occurs over and above a term that is coming from the contribution of a structureless particle that is the basic constituent of my system. So, is this correction important? So, in order to understand that, let us take this example where we try to understand the importance of the structural correction to the internal energy in the case of a monatomic ideal gas, where we know that U trans is nothing but 3/2 nKT and U electronic is dependent on the underlying microscopic structure of the atom. Now, let us consider this example where we have helium atom. So, for helium gas, the constituent particle is a helium atom, for which spectroscopists tell you that it has a singly degenerate ground electronic state and a triply degenerate first excited electronic state, and the difference between the ground and the first excited electronic states is given by around 20 electron volt. Now, then what we can do is we can do a little bit of calculations, and these calculations are as follows. We look at 3 different temperatures, 10 Kelvin, 50 Kelvin and 1000 Kelvin. Okay? And then we know what is the amount of thermal energy kT at each of these temperatures, and we find that delta epsilon 1 2 by kT, this quantity is actually a large number at 10 Kelvin, it still remains large even at 50 Kelvin, but it becomes a finite number at 1000 Kelvin. So, what is the consequence of this? The consequence of this is that this exponential term as written out here, these are virtually 0 at the temperatures, low temperatures of 10 to 50 Kelvin, and this is about 10 to the power of minus 2 at 1000 Kelvin. So, what is the consequence of having this small yet finite value of this term, this exponential term, to the contributions that we see here? So, if I find out U trans, then I find that at 10 Kelvin U trans is about 10 to the power minus 3 electron volt, and then if I go to 50 Kelvin, it remains in the same range, it is just that this prefactor changes. But essentially, just because these exponential terms are essentially 0, therefore, the contribution to U electronic by n, this is going to be 0. Now, when I come to 1000 Kelvin, what happens is U trans is now about 13 electron volt, but as you see that there is some small but finite correction coming from the underlying electronic structure, which is about 0.7 electron volt. So, what is it that we have learned from these numbers? These numbers tell me that, well, at low temperatures, the microscopic states that are being accessed by the system are essentially the ground electronic state of the atom and the ground nuclear energy state of the atom, and then whatever translational motion it executes at those temperatures, that is what uses up the corresponds to the total internal energy of the system in the case of a monatomic ideal gas. Now, as you go on increasing the temperature of the system, what happens is now at much higher temperature, the population of the first excited electronic state becomes appreciable. Now, what is U? U is the average energy of the system. Okay. Now, average energy is nothing but given by the energy of the Rth state multiplied by the probability of the Rth state, and we know that this probability is dependent on temperature. At low temperature, this probability is very small, and therefore, E bar is approximately, so if I can write this as, this is E electronic energy ground state into probability of observing the system in the ground state plus E first excited state into probability of observing it in the first excited state. At low temperature, this probability is very, very small. As a result, this is dominated by the ground state energy. But at very high temperature, what happens is the probability of occupation of the first excited electronic state increases. As a result, then in addition to the ground state energy, we have some energy values coming up from the first excited state multiplied by some number which tells me the fraction of population present in the first excited state. So, this will be the fraction of population in the ground state multiplied by the ground state energy plus fraction of the population in the excited state corresponding to the and multiplied by the first excited electronic energy. As a result, you start seeing the correction terms appearing in the in terms of the internal energy. So, we have now achieved quite a lot, and what we will do is, we in the last lecture for the ideal gases, we will talk about testing what we have obtained. We will use the Sacco-Tetrode equation and see if we have preserved the extensive property of entropy, and we will also check for the extensive property of quantities like internal energy and so on and so forth. And that will be the end of our discussion on monatomic ideal gases, and we will extend these concepts to check for the correctness of the formalism for diatomic ideal gases. Thank you.